All right, so hello and welcome to everyone. Good afternoon, good day, good morning, whatever fits your time zone at this moment right now. We're so glad everyone's able to be here today. We are here for our SciAg Ed Applied Math Ed and Practice webinar, and today we're honored to have Brian Winkel, who's the director of SIMIODE, the Systemic Initiative for Modeling Investigations and Opportunities with Differential Equations, as our featured speaker. Brian's held positions at several institutions, Albion College, Rose-Hulman, Michigan Tech, and the U.S. Air Force and military academies. And throughout his journey as a mathematician and an educator, Brian has been a tireless champion for bringing mathematics to life for students through modeling and applications. So Brian has built a community of practitioners through the SIMIODE devoted to teaching differential equations using this modeling first approach. And please join me in welcoming Brian Winkel as our speaker today.
Well, thank you. Thank you, Michaela, and thank you for the group for inviting me. And it's a pleasure to be here. I see some folks I know, and if we get a chance, I hope to chat. Before we go on, I'll just read my title so you know. It's a ring theory to applied math modeling to SIMIODE with a few stops along the way. And I don't want to concentrate on that too much. I want to get into some applications that you can bring to your classroom. And Michaela has sent out papers that I've written in that regard. So, and if you don't get things and you want things, just ask me, okay? I'd like to introduce Kurt Bryan. If Kurt, you could click your screen on, or yeah.
I'm here.
Yeah, he's here. Well, sometimes some of us aren't all here, but Kurt's always here. Kurt is the author of our textbook, which we'll talk about a little bit later on, and Kurt may engage in some conversations as well. Okay, Kurt is an emeritus professor at Rose-Hulman Institute of Technology in Terre Haute, Indiana, where we both taught for a number of years. So I'm like you. I had a typical undergraduate degree. I majored in mathematics. I was headed for the Lutheran ministry. I was going to be an Alfred Schweitzer and go to Africa and be a doctor and save souls and so forth. And mathematics got in the way. So I fell in love with it. But at the same time, I worked in the food service. I worked in the president's house, sending out mail. When the minimum wage was 80 cents an hour, I tutored in New York City for $20 an hour. So that tells you that. And I was the college organist and the president of the math club and all that. And I went to graduate school. I really wasn't prepared. My undergraduate college was not a solid program, and I almost flunked out. I got a couple of C's in my first year at Michigan State. I regrouped, went to Buffalo. Buffalo was falling apart because the governor had promised Einstein fellowships of 50,000 to all full professors. Then the legislature said to Nelson Rockefeller, who was the governor, listen, Rockefeller, you may want to give him 50 grand, but we're not. And all of the professors were leaving. So I began knocking on doors saying, I was in your algebra class, I was in your analysis class. And I knocked on Maria Wonenberger's office, and she looked up at me and she says, you were in my algebra class, I am leaving. And I thought, all right, goodbye. She goes, would you like to come with me? And I went, okay, where are we going? Indiana University. So there I went. And when I was there, I wrote a PhD on ring theory with Guru Azamaya of ring theory fame. My first teaching position was at Albion College, where I got one job offer. I got one interview, which led to one job offer. How precarious was that in 1971? And within a few weeks, I found out the science library was down the hall. Now, in graduate school, I went to the math library, and IU was pretty much a pure program. So you can imagine the kinds of journals that they got and that which I was reading. And I went into the science library, and there were all of these journals in life sciences and in all this mathematics, in particular differential equations. And at that point, I decided that was a lot more interesting than algebra. And while I taught an algebra course every once in a while, I never really got my passion for algebra subsided considerably, and I went and just did more applied mathematics. I taught modeling throughout and at all times, and I now use the word modeling first And what that means, and if you look at the text that Kurt has written for us, which is now on HTML online, which is a marvelous approach, everything is introduced with a model. The idea is that you introduce a model, you get to some point where mathematics sure would help, and you come in as a knight in shining armor and say, let me introduce this stuff called first order differential equations, as opposed to let's do first orders. Oh, and by the way, we may have time to see some applications. And it's not quite that dichotomous anymore, but that's the way it used to be. Along the way, I founded a journal on cryptology with 4 colleagues, and it's coming up on a 50th anniversary. It's offered free to MAA members, not SIAM, but MAA. And I founded that journal because I couldn't find any unclassified open source literature to teach a cryptology course. I had worked for the National Security Agency avoiding the draft in the Vietnam War. I thought if you go to work for the NSA and we read the enemy's traffic, then you won't have any wars. I mean, where was that naivete going to take me? But I was wanting to teach a crypto course, and so I began, this is BitNet is what we had, trying to figure out other people who had interest, and we decided to start a newsletter, which became a refereed journal, and I edited it for 30 years. And then I founded another journal on college mathematics, microcomputers, because no disciplines had computer literacy. There was no chemistry and computers. And it was the most successful journal I ever founded in terms of finances. I never drew any salary, but I could buy computers and paper and pay my children to stuff journals and, do mailings and things. And I folded that journal after 10 years because it was spread too thin. There was too much specialties that it didn't deserve. And we got an article one day on the philosophical import of the DOS prompt. And I thought, that's it. That's the way, that's too much. I founded Primus, which some of you may know, Problems, Resources, and Issues in Mathematics Undergraduate Studies. It has a capital U, but not there. And I founded that because I was at a large lecture at an MAA meeting in the winter, the big joint math meetings. And I realized the MAA does not have a journal strictly devoted to undergraduate teaching. If you think about it, all the MAA journals are exciting, interesting, eccentric sometimes, mathematics, a little bit about teaching, but not about teaching. And so that was on a Saturday. On Monday, I went home and I called a bunch of friends and said, I'm starting this journal. I need an article from you. I called up a bunch of other friends and I said, I'm starting a journal and we're getting articles. I need a referee for you. And that's how hard it is to start a journal. Okay. So when I retired from West Point, where I was paid an outrageously high salary, I had a lot of money and some inheritances. And so I founded and spent more money than I should have on webs and t-shirts at meetings and everything. I founded SIMIODE, that Systemic Initiative for Modeling Investigations and with Differential Equations, okay? So I want to concentrate on the triple asterisk. That was discovering in the science library at Albion College, the applications of mathematics were just all over the place, and I didn't ever know them. The first application I ever came up with, and I didn't come up with, was the use of sterile male mosquitoes in curbing West Nile virus. And the idea is you sterilize the males, they go out there, impregnate the females, the eggs are sterile, the male die, and you cut down the population. Malaria was the disease, I misspoke, and malaria is still a problem, but not as much as it was. And I remember coming into class, I didn't prep them. It was like second or third class. And I started talking about malaria, and they must have thought, I think I'm in the wrong room, and we built the model and we solved it, and then we had some data and they just loved it. And I knew I was onto something. So that was in 1971 and I haven't stopped since then. So today I want to talk about modeling with differential equations. And they're invented to study change. Anytime anything changes, you can talk about the rate. I'm preaching to the choir here, I know, but That's how I explain it to my in-laws. That's how I explain it. I tell them you go 30 miles an hour, and if you're traveling for 3 hours, how far have you gone? And they go, well, it's 90 miles an hour. And I said, you just solved a differential equation. And they look at me like, no, I didn't. And then I tell them, yes, you did. So you can find all of the material that I'm going to talk about today at our community website. SIMIODE sits as one of the many communities inside Cubes, which is a large uh, project that holds qualitative, quantitative, and biological websites. And we're just one of them with hundreds and hundreds of resources, all of which are free, downloadable, and useful. So I'm going to talk about 5 things today. We're going to go through them rapidly because you can go and find them, but just to give you a taste, and some of you have been to talks, I tend to use the same ones. Incidentally, at the website, there's what we have a starter kit. So if you look at the starter kit, it'll give you some ideas as to how you can start doing that with these resources. And we always welcome authors to write up their materials. We have a referee system. We give you a letter of appreciation and a citation. So you can see, and I'll share with you some others today. So here they are. What can you see from the other side of a mountain? Building a mall, M&M's modeling death and immigration, Torricelli's law for falling column of water, LSD drug model, and my stupid thing here. Oh, there it goes. Okay. Sources and opportunities that you might find. So here's the first project. When I was teaching at Rose-Hulman, we were doing Calculus 3. I was driving from my house to the campus, which is a short drive, and I thought up this problem on the way. And this tells you how reckless I am. I went into class and we used this problem for 1 week. The students didn't know what a partial derivative. The students didn't know what a gradient was. The students didn't know what a tangent plane was. The students didn't know about functions of more than one variable. But with this problem, all of those concepts and many, many, many more, including gradient search, were found. Okay? So here's the problem. And this surface is more than you need. You can take 2 conic sections, 2 parabolic mountains, and they're easy to work with algebraically. But the article I wrote up years later was you put your eye over here at this point where the eyeball, and you want to know how much you can see on the other side of the mountain. That's it, period. I came into class, I stood in front of these students, and I said, what do you think? And they begin, I put them in pairs, and you can see them talking with their hands, like, well, and they would argue. So some of them would argue like, well, if your eye is here and this mountain is lower, I don't think you can see the top, the very, very top. Well, sure you can, someone else would say. So there goes, how do you know whether you can see the top or not? And the other notion is, can you see all the way to the bottom of the valley? Well, maybe the mountain you're on is in front of you. So you can see that they're talking visualizations. And they're also saying, well, to the left and to the right, how much you could see. So we start talking. And one of the things they do rather immediately is they put their elbow where the eye is and they drop it on the other surface. And that's a point of tangency. And already they know something about tangents to curves, and they go, how on earth would we find a tangent and an equation on a surface? So we start talking about partial derivatives and all kinds of things like that. And in this class, we were doing C+ programming, so they actually used programming to do numerical work to outline what you could see. So there's a problem, and this article that Michaela should have sent out, and if not, you can get one from me, describes how I did this. You notice there's no differential equations here. I'm just giving you some examples, okay? How would you get started? What kinds of issues might you invent it with this? What misconceptions do we have? Like you said, can you see the top of the mountain? Does it look like it'll permit a closed form solution? Well, if you give them more parabolic rather than fractions of quadrics, the answer is yes. And how realistic is this situation? And who might be interested in this problem? Well, When I taught at West Point, this became a very interesting problem as in a forward observer for a military advance maneuver. What can you see on the other side of the mountain? Can you see the enemy's headquarters? Can you see a flank movement? So here's some additional tough questions. Find the point on the viewing mountain from which you can see the most area across the valley. That's a tough problem. That's an optimization problem involving numericals and so forth. And I've done independent directed studies with that. For instead of strategic points on the viewing mountain, on the other side, what's the highest point from which you can see these? In other words, if you know what you're looking at, 6, 7 points on the other side, where should you be? And what's the highest point on the mountain? And what's the lowest point you can see? All kinds of questions you can have there. And I had students, even in that calc class, because we had projects, who went back later in that semester to do projects. Here's another problem. I wrote an article called Getting Mauled. And basically, you have a shopping mall. We're going to assume that people travel as the crow flies to make this simple, but you could use taxi cab geometries, left, right, up, down, and that people travel at 30 miles an hour. In 1 hour, the neighborhood of the mall, let's put the mall at the origin, the neighborhood of the mall looks like a circle of about 30 miles. If you're interested in marketing, that might be of interest because there's another mall somewhere else. So you're kind of focusing on this 30-mile disc. But what we do is we introduce a highway which has a 55-mile-an-hour rate right up here across about 2/3 of the way up, 10 miles up. And we'll look at what we want to know is if I introduce a high-speed highway where we let people get off wherever they want. This is naive. That's not the case. There are exit ramps, but just to be so we could get going, you have 55-mile-an-hour road going across this, and people can get off whenever they want. Okay, how does that change the neighborhood of the mall? Well, right away you begin to say, well, people who live far out on the right, they probably could take the highway right into downtown and then get there where they couldn't before. So it ought to expand. And what are the assumptions you can make? And we made very simple ones. You get off wherever you want, naive. How would you begin? Can you identify some points where it's a new neighborhood that weren't in the old? And who would be interested in this? Again, marketing, direct mail, if you knew you had a larger neighborhood. And here's the kinds of drawings the kids make. They kind of know this is like you can run and then you can swim. Uh, and so you could ride along the highway, and at some point you'll drop down here. You won't go all the way over due north of that. You'll cut off somewhere else. And if you start at point Q, well, you'd probably go down to the highway, stay on it a long time, and then drop down. If you start out here at U, well, I'm not so sure how far, but somewhere out here, you could get to the mall. The question is, how far out could you go on a straight line? Right away, you've got a nice problem. So here's the final shape that you get. You get this additional wedge, and all of this analysis is in there, but this is doable. It doesn't need numerical methods, and it's a nice optimization problem, and it gets them thinking. Okay, so I just gave you 2 modeling activities that didn't involve differential equations. What I'm going to do now is just go through some modeling activities that are at SIMIODE. And again, all of these are free, all of these are downloadable. All of these are fully modifiable. So if you don't like the way they are, or you want to introduce some way cool wording, embarrass a colleague or do something, whatever you want to do, you just take the tech version. And there's a few in Word. There's maybe a dozen in Spanish, a couple in German, and 1 in Czech. Okay, but basically they're all in English. There's almost 300 of these modeling scenarios. So here's the picture, and what we're going to do is we're going to use M&Ms. We got a tally sheet. We're going to toss. I'm going to take step 1. We put about 25 M&Ms into a cup. We toss them out onto this plate. You remove the M&Ms which have an M facing up, they die. In other words, they die off from the population. And then you immigrate 10 new ones. So you got it, you toss the M&Ms. If an M shows up, you're dead and out of here, and then you immigrate. First time through, maybe you don't have any immigration. What you have is exponential decay. We just keep losing. And the first thing you begin to ask students is, how many do you think you lose at each turn? And they go, well, if an M shows up, they die. And if an M doesn't show up, they don't. It's probably 50-50. So they lose a half. So they have a decay rate already of 50%. They know they've got vocabulary. Many people, and there have been thousands who use this, do this on the first day of a differential equation. They don't talk about orders. They don't talk about second, first. They don't talk about anything. They just say, let's just do this. And the first thing they get is a difference equation leading to a differential. So let's go ahead with this one that says you toss them onto a plate, you remove the M if it's the M&M if it's an M facing up. And by the way, we don't use peanuts. We use regular M&Ms. And so you talk with students like, why wouldn't you want to use peanuts? Oh, that'd be tough. Could you use other things? Yeah, we could use pennies, gambling chips, a lot of different things, but we use M&Ms. Okay. So then you count the remaining and you record the data and you go back over and over and over and over again. So here's the result, a resulting spreadsheet. Okay. The model that they get looks something like this. B of n is the number of M&Ms. And what happens is at n plus 1, you have 1/2 what you had at n, and they build this model. They've never seen a difference equation, but they say out loud. In fact, I insist they speak out loud to describe so they hear. The number of M&Ms you have at generation or iteration n plus 1 is 1/2 of what you had at iteration n, and we add 10. And then I say, let's get more mathematical. Let's call B of n the number you have at time or iteration n. And then they write this equation, okay? Now, this 0.5 may not quite be true because sometimes M's are printed on both sides in an M&M bag, and sometimes, rarely, there are no M's. They don't get printed. And then there's always the wise ass in the class who goes, yeah, what if the M&M lands on its edge? And right away that guy is shot down because that never happens. The other possibility is it fell off the table. We didn't get, But in general, they'll come up with something like this. And we introduce a general model. We go, well, supposing I don't absolutely know it's 0.5, that coefficient could be A. And supposing I don't know how many we add, that could be B. In fact, one variation of this is you have each student collect data and decide how many to immigrate. So Michaela may immigrate 9, Kurt may immigrate 7, Rick may immigrate 15, and then I have them collect data and pass the data to their neighbor. And their neighbor has to do a model and determine the immigration level. Okay, that works wonderfully, okay? Each student keeps their own M&Ms so that they don't have anybody else's germs, and I tell them they can dispose of them any way they want, and then I wink at them, okay? So here's data in a spreadsheet. This uses Solver, and if you haven't used Solver, you got to look it up in Excel. And basically, what we got here is the time, and this is the data from one of these experiments. This is what a perfect model would do. We start out with 50, we cut it to 25, we add 10. We cut it to 17.5, we add 10, okay? And students don't get hung up over what's a half an M&M. They go, well, that's just a model. There's a difference between them. And we minimize the sum of the square errors right away. And they've seen that in physics and in labs, so they're not too scared about that. Here's where we have 2 parameters, and we try to figure out what the best parameter is. Here's where we have just 1 parameter, and we try to figure that out. And what we do is we use Solver to minimize the sum of the square errors and find the parameters which do that minimization. It's one fell swoop. It's all demonstrated in the modeling scenarios, and you can look them up. So also in that same modeling scenario, we convert from a difference equation to a differential equation. And I found out from many colleagues that they don't do that in their class. They don't show them how they do that. Mainly, they either start with differential equations or maybe they're teaching a difference equation class. But I think it's worthwhile showing them you could start with one and go back and forth between them. Okay, so this is what happens. The data is in blue and the model is in red. And this is a stochastic model. So this is pretty good. I mean, it's not going to fit perfectly, right? So here's another model with M&Ms, a little different. You make a grid and all of this is provided. You can print out this sheet. Each of these squares is the diameter of an M&M. Okay, and what you do is you start with 5 green squares, and those people have a disease. So the paper looks totally blank except 5 green squares. And then you toss your bag of 50 or 25 M&Ms, and if they touch a square which has the infection, they get it infected, and we write a number. So for example, on the first iteration, an M&M landed where that one is right above that green. And what you do is you put a one there to mean that's the first guy that got infected. And then one of them landed here, and maybe 3 or 4 of the first iteration got disease. You pick up the remaining live M&Ms uninfected and you toss it again. You put books around the outside or something so they don't go all over the desk and everything. And you ask students, what do you think happens? Well, at first, you got a lot of available uninfected people, and this disease is going to probably spread pretty fast. But then after a while, almost everybody's infected, and it might not spread as slow. And so what you're building is an intuition for the logistic equation, right? And here's again Excel. This time we actually build a model. And if you look at the lesson, you can do it either way. And this is the solution to the logistic model, where the parameters are K for the carrying capacity and R for the generic growth rate without carrying capacity. So here's the model, and here's the data in the model. And when you use solver to essentially estimate and find the best parameters R and K between your data and the model, this is what you get. The students are very impressed. They're very convinced this is a reasonable model to model that kind of a phenomena. In fact, you get them to trace this curve early on with their hands and maybe on a piece of paper. And I think you've all done something which has a logistic bent to it. And I use the word bent purposely with a pun. And then when they get the model, they can see that, okay? Here's a very common one that a lot of people use, and it's essentially modeling a falling column of water. There's lots of videos that I made in my kitchen sink, and the water falls out of a 2-liter soda bottle. The first time I did this, I forgot about the fact that you need to collect the water. And so I was on my kitchen counter, and all of a sudden my sandals, which only I don't wear shoes, my socks were wet on my sandals. And I went like, did I wet my pants or what happened here? Well, I didn't collect the water. So my wife was traveling. I had time to clean up because it was green floor all over. And I had an iPad with a digital clock. And these kids have all kinds of digital clocks on their stuff so they can collect it. Or you can go to get these on our YouTube channel. You can just go to YouTube and look up SIMIODE. And we have different bore holes, different size holes. Thicker holes, water will go faster. And what you're trying to do is model the height at which this falls. So you ask kids intuitively, some of them say it falls at a constant rate. Others will say, no, 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 it falls faster in the beginning because all the pressure of the water on top. They have their own intuitions. I think most of you have found that physics students have pretty good tuitions, and many of our math students may not have as much. But so they kind of have that. And in this project, what they do is they collect data. They conjure an empirical model. They may think it's a straight line. We'll look at that in a second. They build an analytic model from first principles. They create a differential equation model. They solve a differential equation model. They estimate a parameter. It could be with solver. It could be with anything you want. I taught using Mathematica. You could do MATLAB, whatever, or Python programming. And they compare the model with the actual data. Now, the interesting thing here is this is not a probabilistic model. M&M's was a probabilistic model. So you know that if you want to convince someone that you have a good model, it better do a real good job at predicting. No halfways about it. Okay, so you got some sort of proof in the pudding. Well, here's the data. And this is, I took this off the iPad and then I synced the clock back to zero. So at time zero, it was 11.1 centimeters high. At time 2.187, these timers have time up to the thousandth, which is absurd given what we do with a stopwatch. It was 10.6 meters. And again, you have to determine where you're going to read the height. There's a little menisca. Do you read at the top of the bubble or do you read at the bottom? But be consistent. So here's the time in about 45 seconds, a little less than a minute, the water's drained. And here's a plot. So one of the things is this data comes and we plot it in Excel. It's easy with trend lines. You just slam a straight line through it. And here it is. That's what a straight linear motion. So the kid who says, I think it falls at the same rate is a little bit questioning his or her decision right now because it seems to be steeper at the top and maybe shallower at the bottom. You don't have a lot of data. And by the way, you could go back to that video and you could collect hundreds of data points if you really wanted. So if this isn't enough data for you, just collect more and more data. Next thing is you say, well, it was going fast and then it was going slow, exponential. That's what it's got to be. So you do an exponential and you go, yeah, the exponential, the best exponential kind of bows a little bit too much. It's flatter. That's not that good. You come up with a parabola, could be a parabola. What these are empirical models. There's no understanding of what's going on. We're just fitting the data to the model. And there's nothing wrong with that, but you got to admit that to yourself that it doesn't explain anything. And if we're true scientists, we want a little bit more explanation. Can you articulate why neither of these is great? Okay. So you begin to ask questions. How fast is the column of water falling in the beginning? So you're talking now about taking difference quotients. How fast is something going? Centimeters per minute. They begin to smell differences in differential equations. And if you've been with students who you're doing modeling with, after a while, they begin to smile. Some of them smirk, but they're really smiling. And for large height, the water falls faster. So let's look at some of those rates, okay? In other words, we ask the question, let's put this guy up here. What is the rate, dH dt? Maybe we can't get the derivative, but we can get a difference. So I'm going to go here, and we begin to take some rates. And we notice that at the top, it's falling at the rate of about 0.22 centimeters per second. But at the bottom, it's only falling at the rate of 0.12 centimeters. So it's confirmed. It goes slower at the bottom than it does at the top. And we could plot, and some students do. They'll plot the rate versus time. Some will plot the rate versus height. And now we're getting into really cool difference equations. Okay, they're savvy. But what we're asking for is what can you say about the first derivative? So let's find a model from first principles. I'm going to just whiz through this. It uses Torricelli's law in physics. I'll just show you that. And those of you who teach math modeling course or differential equations know that students who've had some high school or college physics are oftentimes a little more comfortable than students who haven't had physics or who just didn't like physics. So you've always got to be careful and not just assume everybody wants to be Einstein with their physics understanding, and keep things simple. And that's what these materials try to do. So we're not just going to fit a function. We're going to do something more elaborate. And what we're going to do is use a law by Evangelista Torricelli, who was a student of Galileo. And Galileo invented the barometer. Torricelli invented the barometer. And I always like his mustache. I think he's got a way cool mustache, okay? So when you teach this kind of a unit, you can do what I'm about to do. I can tell you Torricelli discovered from lots of study and lots of analysis that this is the differential equation that governs the rate of a falling column of water. That's like, spoiler. Here's the spoiler. Or you can build it from first principles. So what I've done for you, I've told you what the law is. And if we just look at that equation, one of the things you see is when H is big, dH dt is big compared to when H is small. It's negative, but it's big. And G is the acceleration due to gravity. You might imagine it. Gravity has something to do with it. You did it on Jupiter, one thing would happen. And then we talk about this parameter B. And one of the things the students say is, well, it obviously depends upon the hole, the size of the hole. Oh, and it also probably depends on the liquid. If you're doing 1040 motor oil or you're doing liquid mercury, that's going to be different than water or alcohol. So you get it, even when you show them the model, there's lots of things you can get from it, okay? So all of this comes from looking at it, but let's back up and say, supposing we didn't have the model, supposing we didn't know the answer, I'm giving you another approach. Here's what we do. We use a physical notion called the conservation of energy. And at this point, the kids who haven't had physics start to get squeamish. They see the word law, they see the word conservation, they see the word energy, and you say, take it easy. There's two kinds of energies we're going to study. One is potential, and that has to do with how high an object is before we let it fall. And the other one is kinetic, namely, how fast is it traveling? How high was it? How fast is it traveling? Simple concepts. This is one of the tougher slides because what we're saying is the way to measure kinetic energy, physicists have determined you take 1/2 the mass of the object that's falling times the speed squared. We don't develop that. We just say, let's accept that. And then we take the potential energy. It's the mass, it's gravity, and it's how high. Think about dropping a cue ball on your head versus a ping pong ball. Different mass ought to have different potential energy. The conservation law says the total energy at the start of any falling object is the same as it is anywhere along the path. And in particular, if we take a slab of water at the top, the total energy that has is the same as when it reaches the bottom and goes out. So we calculate the total energy at the start and we calculate the total energy at the end. And here's an example. When the water hits the exit, its height is 0 for practical purposes. So its potential energy is 0. It's hit the ground. Here, its total energy is its potential energy is full because we're at the top. And so we do this arithmetic. If you divide both sides by the mass, it's independent of the mass. And what you get is the final velocity is equal to the square root of 2gh plus the initial velocity. And if we just dropped and we turned the water on, the slab of water that we're going to use as our mass is at 0 velocity at the top. So v sub I is 0. So this law says the final velocity going out is the square root of 2gh. We do a little bit of work and we can come back to this equation, the square root of gh, the 2 can be absorbed. You can talk about a bunch of other things. And the point is that you develop this law, this differential equation. So now we have some data. We want to estimate parameters. Okay, we don't need to estimate G if we know where we are. If we're teaching at Colorado School of Mines, G is different than we're teaching at City College of New York or where Michaela is up in the Green Mountains. Okay, so you got to find out what your G is. All right, and here's what we do. This could be the first time you introduce separable differential equations. And it becomes very, very interesting to students because they know if I'm going to get h of t equals, I got to get out of this dH dt garbage and I got to get into an h of t equals. So you give them this approach. You say, let's put all the h's on one side. Let's take the antiderivatives. You know all this. You got an integration constant. This is just the analysis to do that. Finally, you get this equation that the height is, here's all the symbols, B and G, and this is the initial height, but this is T in seconds, and this is H in time and height. And so We do know some initial information and we do know G. So let's put some numbers in and here's what we get. We get a model that looks like this, except we don't know what B is for our liquid, for our tube, for our holes punched in. We don't know any of that, but we know everything else and we don't know what B is. How are we going to do that? Well, what we do is we say, I have one parameter, right? B. And I have data. So if I took the difference between the uh, height at time ti, and I have those all because I collected them from the video, and the model, or I should say it this way, the height and the model, this expression is huge, right? 9 of these squared. I did this in Mathematica, so you don't care if it's huge. And what we say is it's a function of one parameter. And we do a lot of parameter estimation in DE courses with modeling. So this may be the first time you're doing parameter estimation. We want to minimize the sum of the squares and find the parameter B, which does that. In Mathematica, it's find minimum. In Excel, it's solver. You can play with it by hand by estimating that parameter and looking to see how the graphs compare. In other words, there's nothing wrong with fooling with it by hand. So here we are in Excel. And what we're using is we've got the model, which is in red. We've got the data, and the model is a little off. So this parameter is a parameter we're telling Excel, you, Excel, find the parameter B, which makes this model and this data fit best. That's what solver does. And here you go. So it's spot on. In fact, when the students do this, they go, we lost the data. Okay, and I go, what do you mean you lost the data? Well, I can't see the data. And I go, look carefully. And if you look, you can see a little shade of blue underneath each one of them. And they're going, really? It's that good? Then we talk about a physical model versus an M&M model. So this is a great one. And you can give each of your students a different video for different apertures. I use the Black & Decker drill bits. So you can give them a tiny one, thick one, whatever you want. Make your own square one, whatever. And civil engineers know, by the way, if I go back to this, wrong way. They give this parameter, I forget the name of this parameter, but that parameter tells you something about the friction at the aperture. And that's very important when you're dealing with sewage and fluid flow. They need to know that parameter. So they have a name for it. And I apologize, I didn't look it up for this morning. And it has to do with concrete versus copper tubing versus, and so if you've got engineers in there, you say, I want you to look that up for different surfaces and different media. If you're dealing with sewage floods, that's different, okay? Okay, so here's a simple model of the flow of LSD between the plasma and the tissue. This data came from the 60s in Harvard. They asked for volunteers to come in and drop acid. That's what they did then. This isn't Timothy Leary, but it's the same period. And you build a two-compartment model of the plasma where you inject the LSD. They didn't drop it as acid on their tongue. And then the tissue, which is, of course, you're most interested in the effects of LSD on brain tissues, but it's in all of the tissue cells. And you have flows between them across membranes. So you inject a certain amount, and a certain amount is ejected from sweat, urination, just certain parts of the body break down LSD before it ever gets to the brain where it does its thing. And so you have certain velocities and you build this compartment model. And I usually talk about not concentrations, but the amount. So the concentration in compartment of plasma is C of P, and the concentration in the tissue is C of T. Incidentally, this is the most downloaded modeling scenario in SIMIODE. I have no idea why, whether people think I can get some free acid or what, but at any rate, it's over maybe 5,000 or 6,000 people downloaded this. And so you build this linear system. And what this is this is going from one compartment to the other. This is just loss. This one is excretion. And you get this linear system and you have data, same old thing. you solve it. This is a monstrous linear system in Mathematica. Okay, you don't do this on the first pass with a linear system. And you have observations. If you took this difference, it would fill up 20 of these slides, just going on and on. But it has three parameters. Those parameters that are in the down here, K sub A, K sub B, and K sub E, and K sub Ra, if you like that song. But what you do is you have these three parameters and you say to Mathematica, find the minimum. Okay, is it robust? We talk about we're on a parameter surface and you could be in a little low valley in a parameter surface, so you got to watch out, but you have to have a reasonable estimate. And of course, the model at the end has to jive. So we give it some estimates. We get these four estimates of parameter. And here's the sum of the square errors. But here's the proof of the pudding. This is what our differential equation linear system model proves with these parameters. This is the data, and this is what the plasma. And the first time I ever did this, I was amazed because it told me that I can sample what's in your bloodstream and I can know what is in your tissues. So if I'm administering a pharmaceutical drug and it has a certain property and I give it to a pig, I can find out how much is in its thyroid. And let's say we're trying to develop a thyroid medicine and I put an inhibitor in it. I can tell you how much is in the thyroid without killing the pig, cutting the pig up, and checking it out every 20 minutes. Okay? So the beauty of this is you can monitor how much there is in the bloodstream and know how much is in the brain, heart, whatever. Now, there are more modern tools that can do that with probes, but you don't need to invade the body other than a needle. And I did not know that when I started with pharmacokinetic models, which is what this is. And it's a remarkable thing to share with students the insight you can get with a differential equation model in medicine. And this is the plot of the LSD in the tissues over time. And I always like to tell students, it sure does look like you get a high from this. And then it dissipates after 10 hours. These kids stayed in a lab and did this. And by the way, they gave them arithmetic tests every hour. And you can see that initially they scored rather high. And after a while, when the LSD levels picked up, their performance on arithmetic tests dribbled off. And I thought that was kind of nice. They didn't give them a geography test. They gave them an arithmetic test. So that's on our field, Okay, so I've showed you several models, two of which didn't come from differential equations. The others came from differential equations. I'll point out several others later very briefly. So let's talk about SIMIODE itself. This is called a commercial or a plug. SIMIODE is a nonprofit organization. We got NSF funding. I stopped funding it when words like divorce, separation came up in my marriage, and the issue became it needs to sustain itself. So NSF ran a conference on sustainability, and we came away with two ideas, and then we picked up a third one. The first one was to run a student competition, and the next one was to run a conference, and the last one, not in that order, is to publish a textbook for a reasonable price, pay the author royalties, pay for promotion, pay for doing things, and generate revenue, but have a quality product. All of these things fit perfectly with modeling first. They're not contrary to the mission of what SIMIODE. They just generate a little money. So SIMIODE Scutum is a competition that just finished. And as of noon today, all the judges' reports are due. I go through and order them and award certificates. There's no big prize. Teams pay $99 to participate. And we have about 175 teams this year from all over the world. A good number of teams from Ho Chi Minh City, Indonesia, Europe, United States, high school, community college, you name it. We have about 140 volunteer judges. If you want to judge for next year, be my guest. We'd love to have you. I give them 5. The teams have 3 weeks to pick one of 3 problems. They make a 10-minute video. The judges look at the 10-minute video. I give them a rubric and they write a number from 1 to 5, and they write comments, constructive comments, strongly encouraging that. Some write 2 pages of comments. Some write very good. And of course, obviously, I'm trying to get the very goods to elaborate, and I'm trying to get the ones who are writing the great American novel to be more condensed, but that's another issue. So I'm about to do that tomorrow and Saturday and announce the awards. Um, it's just me right now, but there can be more people involved. So that's the way that goes. And you can see the problems if you go to SIMIODE, that page. Then we have a conference coming up in February. It's in its 6th year. This year, we're really focusing on modeling first. In the past, we've done art, we've done AI, we've done lots of stuff. This year, we kind of want to focus, I and my 2 colleagues who were running this, Jan-Ping Ma from Loyola and Tova Brown from Wisconsin Lutheran, and I are running the conference. And we really want to, so instead of going for 2.5 days and having fun and games, we're going to focus on 1.5 days modeling first. Let's talk about how you do it in your class, what goes wrong, what works, how did you enhance it, nitty gritty, that kind of stuff. So that's the second one. The third one is Kurt Bryan. I asked Kurt, well, Kurt will tell you I asked him to do too many things over the years, but I asked him if he'd be interested in writing a text. And Kurt, do you want to say some things about the text at present? What you were trying to do in the text?
Can you hear me?
Yes.
Okay. So I'm in a busy hallway at the moment. We're between classes because I don't have an office being retired. So I wrote the text, so it takes a modeling first approach. Each major topic, each chapter in the book is I like to kick it off with an application that students can appreciate. And then you quickly get to the point where you formulate maybe a differential equation or a system of equations. And then we say, gee, we don't know how to deal with this. What kind of functions would, what's the solution to this? And then we do mathematics and learn something. And then we come back and come to some kind of resolution to the model and make some predictions, validate it against data. The whole thing is based in the way you can get a hard copy, a traditional hard copy, but the main version is HTML based. It's very interactive. It integrates Sage code so they can do computations on the fly. It's got all kinds of exercises in line with the text, end of section exercises, and then lots of modeling projects, some from SIMIODE's website, some I wrote fresh for this. So that's so check it out and see if it looks good for your class. It's only $39, cheap.
Yeah. So we do sell the print on demand copy and the HTML for $89, and but not too many people get that. But it's interesting, the number of students who want a paperback book. I would have thought none of them would want that. They live on their phone, right? But a number of students actually want that. I haven't queried them to find out. So those are our 3 sort of sustainability issues. We got over 400 project ideas. These are not even completed. They're just like abstracts of articles, all kinds of stuff, everything you could want. They're listed by tags. Everything pretty much is free except those 3 things I talked about. You can find lots and lots of stuff. We list other free textbooks. Here's some examples of when I told the students, bring your chemistry book to class. And in the chemical kinetics section, the chemistry teachers rarely do that because they can't presume calculus. So any rate equations they don't have, but the data is in their chem book. So what I did here is you can see what we're doing is a breakdown of hydrogen peroxide. And this comes right from a standard chem book. Here's somebody who did something on modeling eviction. She came to one of our early workshops. Mary is at Wheaton College in Illinois. And there's data on evictions and how it changes in terms of policies. Here's one on the propagation of the word jumbo. It was first introduced when P.T. Barnum brought an elephant into the United States. And Google has data on word frequencies in printed words in the English language. And here you can see up at least until 1940. how the word jumbo began to be used. And of course, now you go and you get jumbotrons, you get jumbo drinks, and it's all over the place. So you can have that as a project. Set students free to do their own projects. Warning, never ever let a student do a project in a differential equation class that just fits data. That's not a viable differential equation model. There's nothing wrong with that, but it does not attempt to explain. By the way, every differential equation doesn't always explain everything that's going on in the physics. I mean, there's not just two kinds of energies. There's atomic, there's thermal, there's heat, so I really make sure, and I don't ever let students get trapped at what I call that lower level of jam data through a function through a data. How do you find resources? Well, I wrote an article on browsing your way to better teaching and how to find resources. And here's conversations, conferences, invited speakers, friends who know about your own interests. They'll send you, they say, hey, Michaela, I know I don't do this, but you might be interested in this application in music. Look at your textbooks and look at the ones that are starred that nobody ever gets to. The authors didn't just put them in there for no one, but most people don't get them. Look for new issues of journals in your, that's how I got started. Back issues of journals that are on the library shelf. Really back issues, like 60 years ago. The LSD comes from the 1950s. The internet, Google search models, older books in your library, online. Sometimes librarians are throwing out math books because libraries aren't used. Online course descriptions at other schools and find out that. Newspapers, magazines, they got charts. They reference them. SIMIODE, there's a concept. Go to professional society. Look at your group's meetings and other things, blogs, government data charts, COMAP, massive sets of projects like that, including math competitions, online support materials, your student assistants, have them look for things. Just say, by next week for our meeting, instead of just grading papers, I want you to go look for some math models that involve differential equations online. You're going to be my assistant teacher, and we may actually use one. Wow, what a challenge. Go to YouTube. Just take a walk through the campus and watch the acorn falls and say, this week there were a lot. Next week there's not so many, then there's none. Maybe next year I ought to collect some data on that, okay? Online data, just galore, right? So work modeling into your classes, all of them, but take your time. Don't try to do too much at once. One time I had a guy say, do you have some modeling scenarios I can use in class? And I directed him to 10 of them. And he goes, how do you do all 10 in one class? And I went like, I don't know what maturity level this guy has, but obviously you can't. So give them something challenging, make it interesting, make it real. Kurt's book starts out with 3 totally different things that converge into one first order differential equation. I won't tell you what they are. You can see the first chapter or 2 online. So go look at that and you'll see. And that really is remarkable. The kids' eyes get wide open. They go, really? You mean that mathematics describes physiology, track, and biology? So here's something, and I published this article. Put your students in the role of a consultant, okay? Come into the class with a calculus problem, an optimization problem. Just take any problem. It doesn't have to be hard. Put a sheet of paper, and this article describes it. This never, ever fails, okay? Guaranteed. You give them this piece of paper before class. You walk in. I've done this at the first day of class at United States Military Academy, where they're expecting to snap and salute some guy, and there's nothing in the class. And this gray-haired guy walks in and goes, is this a Wilson consulting firm? And the piece of paper they have in front of them that I've put there says Wilson Consulting, a client will come and you're to solve this problem. And I pretend to be Jim Wilson. And finally they realize this is the class, there's no military stuff going on here. And they start asking me questions like, what's your problem? And I tell them, oh, my sister-in-law And they go, no, 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 what's the problem? You're here. How can we help? And they go on and on and on. And this article describes how you do that. And when I was at Rose, I would do it in the middle of the semester. Only now they know Brian Winkel. So I would come in as Brian Winkel and I would say, is this the Wilson Consulting Company? And they look at me with a smile and they go, no, it's down the hall. And when they do that, then you've got them in your hand because they have a good sense of humor. So this is a fantastic way to do this. I've had colleagues come to my class as the consultant. I've done drama stuff where I've run into the class out of breath because I couldn't find the room. You can ham it up, whatever you want, and they've got to pull the problem out of you. They got to pull the data out of you. Up until then, every single problem comes from a textbook where they know the data is in the problem. If they don't use a piece of data in the problem, then they know something's wrong. They have to use exactly. When they're talking to me, I am giving them extraneous data like you wouldn't believe, like my sister-in-law, the dimensions of the plant has nothing to do with that. The union bargaining, just, and finally some kid will say, what actually do you want us to do? I mean, I'm babbling like I do now, but this never fails. Trust me. Okay. So that's my final set of comments. And I'm leaving you with this set of differential equations. Okay.
Thank you. Thank you, Brian, so much.
Okay.
I wanted to open up the floor for questions. I know that I think Patience had put a question in the chat just about the SIMIODE Expo.
Yeah, the SIMIODE Expo is every February. And if you go online at our website, we're soliciting talks now. We have an interest in principally focusing on practical models that you could use or have used in class, or maybe sources of data and how you use them, sort of the nitty-gritty of how you teach. And there's an early registration fee of about $65, and after that, it's maybe 95 or something like that.
Yeah.
It's a
Well,
day.
and just to clarify, so is this only open to people in the US?
No, it's open
Okay.
to anyone. There's time zone issues,
Okay.
but we have people from New Zealand who routinely come. We've had people from Japan presenting. They're live. We capture all the talks and put them online. And in fact, if you want, and you go to our website, you can see all the talks from all the previous conferences, including the keynotes. We're not doing keynotes this year. We're just going to do, just concentrate on talks. We've had wonderful keynotes, AI, magic, art, um, you name it, social science issues, ethics issues, ethical modeling. And but we are concentrating on this practical aspect. And it's Friday afternoon. It's, I think, uh, Valentine's weekend, Friday at noon to 9 o'clock, and then Saturday noon to 9 o'clock. So, it's fair to US mostly, obviously, but we've got some loyal attendees who just love coming in from down under and out over.
Are there any other questions or comments?
You can always write to me at director@simiode.org. You can find anything you want in SIMIODE at that website. And if you can't, let us know. We'll try to accommodate. One of the things we would like, and we don't ever get, we have been in existence for 13 years, okay? We have hundreds of modeling scenarios. I meet people at conferences who say, oh, I use that all the time. We have thousands and thousands of downloads, thousands and thousands of views. Not one person ever has commented on any of these resources.
Ah, So what would it be helpful if people were commenting specifically in how they were using them and modifications that they made and things like that?
Yes, and in fact, my image was to build a community of practice. The word community doesn't exist at SIMIODE. I'm embarrassed to say that because if Ariel uses it and says, I did this variation, then Kurt, when he downloads that, looks at it and reads, I never thought of that. That wasn't in the original. That was what I wanted
Yeah.
to have. And not only would Ariel and Kurt then know about each other, they actually might talk to each other. They might say, maybe we could join teach. I had these great visions. It's just never happened. And I don't know whether it's me, my age, my generation, or the way we present things, but we have comment capability in but I talked to
Okay.
Ken Galusa, who runs COMAP, and they have the same issue. He knows people use it, but nobody ever,
Nobody's commenting. I'm
yeah,
guilty. I'm guilty of that. I've used some of these.
don't
I
do it.
should
Don't do it.
should
Don't do a guilt trip on yourself. Maybe we don't feature it prominently enough. And but and we don't, I mean, our egos are not such that we need Michaela going, oh, it was the best thing since sliced bread. We need Michaela saying, it was really good. And I'll tell you why, because I had a kid in the back of the class who didn't give a damn about anything, but boy, he sure woke up when we realized, you know, or whatever. Now, these are public, so you don't want to mention names.
Right, right.
Uh,
But it would be helpful if people were saying how they implemented it and maybe little tweaks and things that they tried that worked.
Yeah, yeah, and here's a variation. Incidentally, all of these resources have what we call a teacher version and then the student version. The student version is anybody can use it. The teacher version is when you register at SIMIODE and identify yourself as the teacher, we give you access to the teacher version. What does that mean? It has all the student version stuff, but then it has comments from the author with I used it this way. I didn't do this. Watch out for this. It took 2 periods. I thought it was only going to take one, whatever. And some of those author notes are, um, uh, I stole this from Kurt's text. I modified this. I wrote a Python code. You know, so and that's what we'd like to have. We'd also like to have it so that you could add. So if you were writing in Python, and we have Maple and Mathematica, well, Python, the price of Python is infinitely cheaper than MATLAB and Maple. That would be nice. Okay. Yeah. So uh,
Yeah.
someone else has a question from Central Asia.
Yeah,
Hi.
good day. Thank you very much for a very interesting presentation. I'm representing University of Central Asia, and I am teaching different math subjects. My specialty is differential equations at University of Central. My name is Khalik Nazar. I'm from Tajikistan, and somehow I found out that our Central Asian countries are not in the list of, when I tried to register for this conference, let's say the list of so-called developing countries. Will you include it or it will be included by someone else? This is the first question. And then the second question, if I may. I'm teaching sometimes these differential equations and other subjects to non-mathematicians, let's say majoring in environmental sciences and economics, and they don't have a solid background in calculus 1, calculus 2. What would be your approach for those, let's say, non-major students? I understand that there are some simple calculations with example that you demonstrated today. It's just the basic calculation, finding the least squares, but still they need some, from my understanding, some understanding of the calculus. Yeah, I would be very glad to hear your appreciate your points of view on this. Thank you very much.
Well, first of all, the first question, we for Scudem, we use a list of developing countries that was USAID. And our current demon, who's the president, wiped out anything that's USAID. There's no more agency even. So we had a list of developing countries that included India. We can't use that list anymore. It doesn't exist. So we use the developing countries list from the United Nations, which does not include India as a developing country. So I'm not picking on India, but if you think about India, they send rockets to the moon. They have an atom bomb. You would not call them an underdeveloped country. And yet the economic level to pay $100 for a student to participate in anything, 100 US dollars is outrageous amount of money. And I'm not insulting your country or any others, but I'm just using India as an example. And so we have to struggle. And usually folks like yourself write to me and I go, yeah, sure. It's not, don't worry about it. Don't pay. Okay. But I just had to use some list as an initial screening, and that's a sticky issue. What we wanted to do is extend our offerings to places where money is at a premium. I went to graduate school, and many of my fellow Indians and Pakistani students, $1 in the US buys $7 worth of food in New Delhi. Okay. So they were sending money home all the time. I understand that. Okay. So we try to accommodate. And when people ask, if some guy sends me from London, England, I go, listen, bud. But in general, we try to be very because we want to extend that hand to you. So if you're involving in SIMIODE, just drop me a note, okay, at any time. The
Thank you very
second thing
much.
is a lot of data you have in economics and social science is presented visually, okay? And you can estimate slopes. You can get ideas from calculus rather quickly from data. And you can get functions to fit in Excel, like you said, least squares. And you got to be gentle, but you can say, how fast are things increasing here? And of course, the social scientists want to know why they're increasing fast. So now you've got a parameter, a causal something that's driving it. The GDP went down. Access to heavy zinc got cut off because China did something, whatever the political thing is. And so it's always good to tie a mathematical thing to something that they like or they're interested in. They're interested in the politics or sociology. And calculus, well, we can say this. Calculus isn't that hard. It's about how fast things are changing. And if you keep it in that vocabulary and you don't keep dropping words like, well, this is a first order separable differential equation. I mean, that's the kind of thing you tell when your mother is bragging about you to your Aunt Louise. That's the kind of thing you speak to just impress the hell out of your Aunt Louise so she'll give you 25 bucks and cookies, right? But you don't use those words on your students. You got to use simple words like up, increase, slower, faster, and get them to articulate that. And then maybe bring the calculus vocabulary in. Well, how fast is it changing? Let's look at a difference, the change in GDP versus time. Okay, they can do that. And they know about miles per hour or kilometers per hour, right? They know how fast things are going. So they know about a rate. And they know that with their little motor scooter, they can really rev it up and accelerate. So they know that word acceleration, but they don't know what it means. Okay. And what it really means is the velocity, the speed is changing. So now you got a change in distance versus time. And then you got a really complicated thing, a change in acceleration. Of course, if you want to do change in acceleration versus time, you got this thing called jerk in the English language. But you have these things that are in their heads, but they're not clear. And so you can be the hero by clarifying concepts they already have, and they already have a vocabulary for, but they don't know what they are. I don't know, is that helpful to you?
Yeah, thank you very much. Very interesting. And And if I may, I have one more question,
Sure.
if it's okay to ask one more question. Nowadays there's trend of AI is going on, and we always, I mean, the faculty members of different courses, different subjects, they have discussions always on this. And what is your point of view in terms of integrating AI in modeling? I understand from my perspective, there are pros and cons for this AI. Especially, I usually tell my students that when you use right away AIs for solving, let's say, word problems, it stops you, thinking basically. And m- that mathematics is not just, for playing with the symbols, but improving the critical thinking skills and reasoning skills. So,
Yeah.
what is your point of view on
So,
this? Thank you.
so my son teaches entrepreneurship. My son lives in the AI world. My son was a keynote speaker at this conference several years ago on AI. And he was so proud to tell his dean that he talked at a math conference and he teaches in the business school. But his philosophy is it's here, get over it. It's not going to go away. Now, the question is, okay, don't be such a smart aleck and say that. What are you going to do? And that's what you're asking. It's here. What are we going to do? Well, one of the things you're going to do is when we went from scrolls to books, you had to learn how to open the book versus a scroll. When we went from handwritten to typewriter, you had to learn how to effectively use a typewriter. When we went from typewriter to computer, it goes on and on and on. When we went from um, Fortran to Mathematica, you had to know how to use it. And we figured out that. And we're going to figure that out. And one way is to say, fine, use it. Now, spend half of your paper that you're going to submit telling us what you did, how it changed your point of view, what you learned from that. Now, the bad news is you can ask AI how to do that as well, right? You can have AI do a meta analysis, right? I think it goes on and on and on. But after a while, you get it's kind of like cite your references, but do more. So my son's philosophy is, and I'm not teaching. I haven't been in the classroom since 2000, and I don't even remember. But um, yeah, it's a tool, but describe with pride how you used it. What did it do for you? What, where did it go wrong? And early on, they went wrong with mathematics. Okay, they're not doing that so much as much as they used to. They're getting it right. Um, and then say, another thing you would say, if I was in the class, I would say, push it further. Don't just do the problem I gave you, which was linear. Push it to do something nonlinear. What would make your model nonlinear? Okay. Now, again, the student could ask, tell me how to make my model nonlinear. I mean, but if you keep asking them enough questions, they're going to sit there and go, okay, how do I make this nonlinear? They'll actually take a little bit and do that. Okay. Um, so push, you know, you don't have to encourage the use. They're going to do that. But I hated it when teachers were teaching with TI calculators. The students were learning stuff, and then they came to the exam and they said, you can't use a calculator. I mean, what is taking square roots by hand on an exam going to help, right? That's ludicrous. And the same goes with AI. I think, I mean, the next mode of thing is going to be mental telepathy. I'm going to think something, and you at Central Asia are going to think the answer, and we're never going to write anything down. And we're going to think it, and our professor is going to think the same, and that's going to be the end of it. And then we're going to think our grades over to the registrar, and then they're going to think a degree up, and no one's going to write anything, and we're going to have to deal with that. And AI is going to look like kindergarten compared to the next stages. But it's worth worrying about. It's worth being concerned about. My brother teaches English 101. Think about freshman English compositions, right? But if you've ever used that, you can smell AI, right? You can smell the taste. I'm corresponding with a lot of people in Vietnam. We have a good number of Vietnamese participating in our Scudem. And the emails they send back, with all due respect to their English, which is wonderful because they have to do a 10-minute video, their emails they send back are written by the King of England. And it's not. It's not a sophomore college Vietnamese student. But I accept that, and in your part of the world, Indians will write most honorable sir. They will write that. They don't need AI. That's just the way they write, and so I accept that. I don't say, look, just call me Brian. No, they can't do that. It's got to be most honorable, important sir, and I write back, hi. So,
I think
Thank you very
Ariel
much.
had a question or something to add.
Yeah, a comment, a follow-up with this AI conversation. The AI, without data, there is no AI. The AI that we're experiencing is all the data is the input, and without data, there is no AI. So as far as integrating or modernizing the differential equation class, having data literacy skills is a very powerful skill. So it's not like your ODE class has to directly have a module on AI, because I would suggest if you could bootstrap the data literacy and how like data is so powerful, you are addressing in a way, you're kind of definitely modeling and data, they go together, and I guess also if I can contribute to the populations you were talking, that are students that are perhaps not engineering students, they're not in the traditional calculus pathway. I think for those populations, the way they would do numerics is very important. You're not going to spend time with a lot of derivations or proving theorems and stuff like that. It's not going to be very theoretical. It should be very applied. So Python, R, Jupyter notebooks running for R kernels or Python kernels, those could be, I think, very instructional, very useful instructional materials. But even if you're using Jupyter notebooks, sometimes it's tricky if they're using Anaconda on a local install, or if they're running the Jupyter notebook hosted on some, maybe your university has a way of hosting this. So for the instructor, there are a few things to figure out there, so that this could be as smooth as possible when presented to your students. But like Desmos has something called the Desmos graphing calculator, which Desmos could do some least squares. But I guess like Excel, you have to have the functional form for them to fit a scatter plot. But when you need to solve the differential equations numerically and then feed the numerical solution, that's when you need something like Mathematica, R, or Python, because it's a little more sophisticated. But yeah.
One thing is we have a modeling scenario on the spread of an oil spill. So you might want to note down the spread of an oil spill. And it's just data. Okay, simple data. I'll tell you what it's about. So you have a photographer that goes out and takes the picture of an oil spill in the ocean. And then 10 minutes later, from the air, takes another picture. They bring those pictures back, put it on a grid, and they determine in that 10-minute interval how much it's spread. And then later on, the photographer goes out again, takes the picture in 10 minutes. But he never writes down when he took the pictures. All you know is now, 10 minutes later, and then sometime later, now, and 10 minutes later. There's another variation where you're collecting data in a chem lab and your buddy is at night playing games and he forgets to write down the time, but he writes how much and then how much 10 minutes later, but he never tells you 3 o'clock, 4 o'clock, 5. You don't know what time he's collected it. So that data is there. That data frustrates students so much. They can't plot anything against time because after the first 10 minutes, they don't know when it occurred. But if you start taking differences and looking at the change and how fast it changes, that's students will do that. And I've done this in class, and every single time you do this, there's always one student. It could be the kid that sits in the back of the row and doesn't do anything. He goes, if you just look at how fast the oil slick is growing, that plot's kind of interesting. And of course, what it does is it goes like this. It gets thinner and thinner and spreads out. So you could then fit a curve to that. So you could take that data from any economic parameter you want and just delete the dates. In other words, don't tell them the dates. In other words, you got data from 1900, don't tell them 1900, just 10 years later, it was here. And then sometime, I lost the book, but I want to know what the future is going to be like. And so predict that. But that's a way to get kids who are sharp in differential equations very mad at you because they're going, we can't do anything with this because you keep telling us you got to plot against time and I can't plot anything against time. And I go, I don't know. You just got to figure this out. And if you look at that modeling scenario on the oil slick, I wrote a paper on that because I've been using this thing for 30 years. And each year I do this, students come up with something different. It's unbelievable what they will do. And if you tried something like that with any data you want, you don't have to use mine. You would be surprised at what they will come up with, and they will feel good about it. And by the way, you could write for SIMIODE an application on that if you wanted. But so Ariel's right. Data. And AI uses data, generates data, but even if you don't have that, you just go to books.
Well, it's time for us to wrap up. Let's thank Brian one more time.
Thank you.
So thank you. Thank you very much, Brian, for spending the time with us today. And stay tuned for more webinar events from SciAgEd. And thank you so much for joining us, everyone.